Okay, in this video we're going to come at the Laplace's equation, the approximation of it from a different angle. It's kind of a different way of deriving Laplace's equation, and it's something that there's no harm in you being able to do. Okay, so we have something called a harmonic function. Now, a harmonic function, it's a function of two variables, so it's kind of defined on what you might call, well, I don't know, a domain or something. I'm not sure exactly what it's supposed to be. And if you have a particular point, which in a minute I will refer to as x0, y0, a harmonic function has the property that the value of the function at a point is the average of the function on any circle. I'm really struggling to draw a circle here. Okay, let's just do a crop circle. Not a crop circle, a crop circle. That's supposed to be a circle. So it has the property that, so we're going to call this the circle. And this is the point x0, y0. So it turns out that, this is a definition of our, well, there's different definitions, but this is, okay, we don't know what a harmonic function is, so I'm not too bothered about that. So u of x0, y0, so that means the value of the function at the point is equal to the average value of the function such that you average over the circle. So let's slow this down for a moment. So you've got some function that's defined on a domain, which I'll call D. And it has the property that if you take any interior point on the domain, say this thing, and draw any circle around it such that the circle is inside the domain, then if you average the temperature on this circle, you get the average of the temperature at the center. Now there's questions here about how do you average on an infinite set. Well, you should have looked at something called mean values in one of your maths modules in first year. I won't go into here. It basically involves an integration. Now, because an integration is an infinite sum, you're averaging over infinitely many things. Okay, so that's how this could make sense. Now, I'm not too bothered by that. What you can show mathematically in analytics, so it'd be something like, even beyond what you do at Marina, if you did a maths degree, you would show this, that solutions of Laplace's equation are what are called harmonic functions, and they have this property. And so basically what it means is, take a plate, essentially what we're talking. Okay, we're coming at a few different angles here, right? We know that the temperature distribution is a harmonic function. Okay, let's do some grid lines here. So let's do this grid, this grid, this grid, this grid line. Now, if I drew this properly, which of course I did not, we know that the temperature at this grid point here is the average of the temperature on the circle, or any circle, centered at that point. And what you can do is, if you make the grid points, or the grid a square grid, you can say, rather than averaging the temperature on all those infinitely many points, why don't we just take 4 of the points and average those, and the 4 points you'd be interested in be this one, this one, this one, this one. And so you'd say something like the temperature, and we're going to call it, I think, Tk, well, no, Tij. So let's say this is I along the x, I delta x, and this is j delta y. The temperature at the middle is the average of all the temperatures on the red circle, but let's just take 4 of those infinitely many points. So this one over here is +1 in the x sense. Say this one up here is +1 in the j sense, which is the y sense. This one here is back 1 along the x. And this one here is down 1 along the y. And average these out. And this probably really should be an approximation now. So this is kind of saying, okay, we know that solutions of Laplace's equation are harmonic functions. So that means that if you write down a grid, take a grid point, the center of this, that we know that the temperature here is equal to the average of the infinitely many temperatures along the circle. And what we'll do is we'll approximate it by saying, okay, we'll just take the 4 of them. Okay. Now, the idea now, think now again about just temperatures. So this is saying that if you've got a temperature at a point, it's just going to be the average of the temperatures around it. So along a rod, the temperature at a point should be roughly the average of the temperature, say 1 centimeter along the rod and 1 centimeter back the rod. If you've got a plate like this, the temperature should be the average of all the adjacent temperatures in a certain zone. So this should be, you know, if there's hot to your right, cold to your left, you should be the average. If there's hot up, hot down, cold left, cold right, maybe you should be the average of those. So this suggests that you could actually use the mean value property to derive Laplace's equation in the first place. Now there's all kind of logical errors going on here, but really what I'm interested in is people being able to work with finite differences and stuff like that. Okay. So what we showed in an earlier video is that when you're in steady state, the heat flux into any element equals the heat flux out, and we said heat flux is proportional to difference in temperature, and we derived the mean value theorem. Excuse me, we derived Laplace's equation. So we take another approach, take the mean value property as the assumption. So assume that this is the thing that temperature obeys, that the temperature at each point is an average of temperatures around it. And write this down, and then you can, it's saying that if you write Tij, okay, there's a bit going on here, it's a little bit messy. Oh yeah, so actually the thing that I often ask isn't to take this and derive Laplace's equation, but you can do it, is actually take Laplace's equation and derive this. So this is just kind of another way of writing this. This would be, okay, you've got your point. This really should be t of x, y. And this should really include y. This should include y as well. This should include x. And this should include x as well. And basically you can rewrite this equation like this. And then, is this accurate? Not really. You need to take the delta x and the delta y to get really, really small to make it accurate. And this, of course, is next minus current over difference, next minus current over difference, the rise and runs, rise over run. This is a rise over run in the x sense, this is a rise over the run in the y sense. And basically what this means, therefore, is that if you take the limit as delta x and delta y goes to 0, these are derivatives. And because you've got y constant here and x constant here, what you're dealing with actually is partial derivatives. And actually, now that I write it, I realize this just does not make sense. I'm afraid this does not make sense. You cannot write it like this. What you possibly can write it as, so thankfully I can actually write the proper version now. You will be able to write this as t of x plus delta x minus twice t of xy plus t of, and this should include y, t of x minus delta xy over actually delta x squared. And then this one should be the temperature at x, y plus delta y, minus twice T of x, y, plus T of x, y minus delta y, all over delta y squared equal to 0. Okay. Basically just undoing what we did earlier on, and then you take the limit, and this is Laplace's equation. Okay. All of this analysis, no matter how you come at it, boils down to that the way we're going to think of it is the temperature at each point is the average of the surrounding ones. It also follows true for a three-dimensional steady state temperature. The only difference being is that the array of temperatures is three-dimensional, and so how many, if you think about a three-dimensional grid, how many internal grid points should there be? Well, you've got up, down, forward, backwards, left, right. There'll be 6 of them. Okay. You might say, why didn't we just do this in the other vectors or other lectures about Laplace's equation? The reason being is that we want to talk about heat fluxes, and also the mean value property doesn't hold for all partial differential equations. Okay.